particular kind of fish can be. Okay? Thank you.
Well, thank you, Diletta. The floor is yours. Please.
Good morning, everyone. My name is Diletta Olliaro. I'm a second-year PhD student in computer science from Foscari, University of Venice. My supervisor is Professor Andrea Marin, and my primary research focus is in performance analysis with an emphasis on techniques that take advantage of queuing theory. But as this speech will reveal, I'm deeply passionate about everything that concerns networks and their modeling. I'm trying to start with giving some backgrounds on queuing networks and queuing theory, and then I'll try to give a glance on all the research directions I'm currently working on. Okay. Performance evaluation is the science of assessing system efficiency, responsiveness, and resource utilization, whereas queuing theory is a powerful mathematical framework for analyzing and predicting system performance. Queuing networks are mathematical models used to study the behavior of systems characterized by the processing of entities, usually referred to as jobs or customers interchangeably. We will refer to a customer when denoting everything that arrives to a facility to require a certain kind of service, and we will refer to a server as whatever facility that is able to grant this service to the customers. Queuing networks are used to describe a wide range of real-world systems. For example, we can think to distributed systems that are composed of several components that need to interact and coordinate and communicate in order to provide to a final user some service. But they also have been used for telecommunications, for determining the sequence of computer operations, and for evaluating scheduling policies. They've been also recently used for health services, for example, for the policies for hospital bed assignments, the scheduling of appointments, or even patient flows. And they can also be used to better design the layout of manufacturing systems, for example, to optimize the line of production and of the inventory management. These models actually have found a broad application in telecommunications since the pioneering work of Leonard Kleinrock. You can see he was a very passionate researcher about this topic, as he even wrote a poem to queues, of which I will cite just a little piece, because I think it embeds well the importance of these models. If you want to model networks or a complex data flow, a queue is the key to help you see all the things you need to know. This, I think, is particularly interesting and true because once we are able to model a system as a queuing network and we know the tools that queuing theory provides us to analyze it, we can find out everything we need about their performance evaluation. The benefits of a queuing model are threefolded. They enable to estimate and predict the system behavior under different conditions. They can be used to identify bottlenecks, to balance workload and consequently optimize resource allocation. And finally, they also provide a decision-making tool as they enable designers to make informed decisions and choices about the system planning. Key ingredients of queuing networks are usually given, are queues, of course, and they're usually composed by a waiting area that we will call buffer or queue interchangeably, and by a service node that is actually the facility with the computational power to grant this service. Usually, queues are described by their arrival and service processes, which are usually stochastic or even Markovian processes because they need to embed the randomness behind these systems. Then we describe queues by their number of servers available, the total capacity of the queues, which is the maximum number of customers we allow in the buffer, and the population size. Then we need to have a routing matrix, which in a queuing network context tells us where customers need to go after they receive the service from a queue. And these, in the future images you will see, are usually denoted by arrows connecting the stations. Then we also need to define the service discipline, which is the order in which we serve customers. We can think of the easiest first come first serve that I think we all know, but we can also go on more complicated disciplines that include preemption or even dropping and so on and so forth. Finally, queuing networks can be either open or closed depending on the fact if we have an arrival process coming from the external. In that case, they are open. If we do not have an external arrival process, we are in the case of closed networks where the population of customers is finite, and consequently the study of the networks relies on the study of the dynamics of these customers in the network. When studying queuing networks and talking about performance evaluation, we are particularly interested in these performance metrics. Utilization is the fraction of time a server is busy serving jobs, and it denotes how efficiently servers are being used. Throughput is the rate at which customers complete service and exit the queuing system. Usually a higher throughput means we are having better performance from the system. Then we usually study queue length, which is the average number of customers we have waiting in the buffer. And finally, we usually study waiting time and response time. Waiting time is the average time spent by a customer waiting in a queue, whereas response time is the sum of waiting time and the average time spent by the customer in service. Notice that these two last performance metrics are particularly important when evaluating quality of service. Two last things about background. When we study queuing networks, we usually hope to find them to be in product. We hope they are in product form networks. This is a special case where the stationary probability of the whole system can be expressed as the product of the probabilities of its components. The advantages of these particular solutions are that they enable us to study component in isolation, which is much easier with respect to study the whole complexity of the entire network. Then they allow the efficient computation of the performance metrics we just saw, and they give a very accurate and efficient results. Of course, this type of solution also have limitations. Because we need to usually do some pretty limiting assumptions, like for example, sometimes we assume the exponential distribution both for arrival and service processes, and they require a great theoretical effort and understanding of the underlying model in order to be proved. One last concept is to highlight why product form solutions are so important is that usually when analyzing queuing networks, we face what we call the state space explosion problem. As the state of a network is usually given by a vector, which length is equal to the number of stations in the network, and the elements of this vector are given by the average length, by the length in that precise moment of every queue. It's easy to understand why, as the system increases, this space of states actually increases as well exponentially. This is why product form are so important, because they enable us to find solutions even without generating the whole state space, which instead would be required in other cases. In this way, when product forms hold, we can apply this particular algorithm that is called mean value analysis to retrieve performance metrics, which is a very efficient and recursive algorithm, which again does not require the state space generation. This is the overview of my PhD up to this moment. During my first year, if it's possible to say so, we completed the literature review phase. Then we presented a product form model that was, at the best of our knowledge, unknown to the state of the art. We continued studying another particular queuing model, which is the multi-server job queuing model. Then in May and June of this year, I was a visiting PhD student at INDEA Networks Institute in Madrid, where we started to study real-time mobile gaming environments. And I'm currently working on two more projects. One is a network-friendly recommendation system based on similarity caching. The other one is to propose a modeling approach for quantum key distribution networks. I will try to give a glance on every one of these except the last one, because quantum key distribution networks require a lot of background and related works explanation. Starting with fetching queuing models, we have that traditionally queuing networks usually present state-independent routing, which is what you can see in this animation. It means that the customer arrives to a queue, usually wait a certain amount of time, then gets into service, and it continues this process over and over again. The particular thing is that usually when a queue is empty, if there is no one to be served in the buffer, when the server gets idle, it remains idle, nothing more happens. Fetching queues are quite different. To underline this difference, we draw the buffers vertically instead of horizontally, and we will call them warehouses instead of queues. In this case, the routing is state dependent, and every queue has a set of providers. We will call, for example, this one is a provider for this queue because the probability of going from here to here is greater than 0. What happens in this particular kind of queues is that when a server gets idle, if he has someone in the queue, he takes his jobs and starts to serve it. Otherwise, if its warehouse is empty, it goes and asks to other providers if they can give him a job. This procedure goes recursively, and as soon as he finds, like in this case, a job, he takes it into service. This policy makes so that the servers of these networks are never idle. So this policy is actually maximizing the system throughput. The starting point of this job was actually given by two authors, David Gates and Mark Westcott, which in 1994, during a collaboration with Queensland Railway, designed a very particular Markov process for modeling the process of wheel replacement and restoration of the trains of the company. The interesting thing about this model is that they provided a product form solution, but only for this particular topology for the network, meaning a tandem topology where there are no branches, no cycles, no confluence, no nothing. They were able to derive the product form solution, but they had to use some techniques that required some very heavy algebraic computation. Our contribution was to give an easier proof of the product form result using a particular theorem that actually provides a very simplifying and elegant approach. We were able to prove that the results holds for several topologies. Actually, every topology we could try with branches, cycles, confluence, and so on and so forth. And moreover, the thing is that usually in related works, these kind of strategies have been investigated for load balancing, which means that we are usually moving jobs to equivalent servers that have less workload. In this case, we are actually kind of avoiding service stage in order to keep the throughput of the system very high. So this also was a novelty about the study. The applications of this kind of model can be given by distributed system for image processing, where we apply filters in cascade. Of course, if a job skips some service stage, the result will be less, the quality of the result will be less than in other cases, but we will still have a result. And this can also be this type of model can also be applied in case of, for example, some hardware components like lithium batteries that whose efficiency decrease over time, and we can think, for example, of a station that regenerates these batteries and some other devices that needs it, steals from it, even if they were not completely regenerated at that moment, but they have sufficient energy left in order to provide energy to the device requiring them. In general, this kind of model can be applied to any system where successive refinements of jobs is required. is not required. It enhances the quality of the result, but is not strictly required. On this line of research, we started to investigate this model using stochastic Petri nets, which are another formalism that gives, which I won't go deep in it, but gives a more rigorous and formal semantic to the underlying semantic of the model. Doing so, we discovered a very nice duality property with these kind of networks that are known in the literature as skip-over queuing network, because they are intended as finite capacity, and when a job arrives into a buffer and finds it full, it just skips over that network. This is another case where the routing is state dependent, because we have a probabilistic matrix, but then according to the state of every queue, we can go in different stations. And the product form result for this case was already proven. But the nice thing is that, as I anticipated, we were able to prove that there is a duality result between these two models, which means that we are now able to compute the performance metrics for one of the two, and constructing the other dual network, we are able to directly compute the performance metrics for the other model in a very straightforward manner and just applying some very simple formula. This job was a joint work with my advisor and Professor Sabina Rossi from Foscari University of Venice, the first part. The extended version had the valuable collaboration of Professor Giuliano Casale from the Imperial College of London, and the duality result was a joint work with Professor Gianfranco Balbo and Matteo Sereno from the University of Turin. Going on to multi-server job queuing model. We have that recently the nature of the jobs we are studying has changed. Traditionally, queuing theorists studied jobs that required only one server at a time. The thing is that nowadays this is no longer feasible. Queuing model still represents well-server facilities, but not the jobs, because now users usually require resources for mutable durations and also in different quantities. This is particularly true in the case of video streaming through packet networks. For example, a user could require where users share the data transmission rate, because, for example, one may be watching a short episode of a miniseries on Netflix, and another person may be watching a whole movie. But that's also true for data centers like those operated by Amazon and Google. Because they have very large tasks that could take different processing facilities for variable amounts of times. These kind of very contemporary systems can be well described by multi-server job queuing models, which is actually listed between the open problems of queuing theory of today. This is why we started to study this kind of model, which have a very particular dynamic that I try to animate, and now we'll see. We divide jobs in different classes, for example, red, blue, and green, and each one of these classes takes a variable, takes a different amount of servers and for a certain amount of time. In this case, they are served according to a first come first served policy. But the use of this policy results in the fact that we may find the system in a situation in which, like this one, the last job in the waiting line does not fit. So we call it the head of the line blocking. Of course, these jobs, in order to be served, and all the subsequent one will have to wait that all the previous arrived jobs have been served. This, of course, complicates more the model. We studied this model under three assumptions that actually still hold practical validity. We assume to have just two classes of jobs, big and small, but we discovered that this can be a good approximation in the case of database management systems, where we have where we have queries for database updates, and that can be described by big jobs, and read-only queries that can be described by small jobs. We decided to study the system with the first come first served policy. Firstly, because other policies have been already investigated. Secondly, because even if the whole blocking degrades a bit the performance, because we are not using at its maximum capacity all the servers available, we add that when if we don't imply preemption, which can be very costly in case of in the case of virtual machines, for example, we will soon arrive to the point where big jobs are in starvation. The last point, the last assumption we made was to study the system in saturation, which means that we are assuming to always have jobs in the queue that are waiting to be served. This is also particularly a practical thing that is used, as far as we know, in database management systems. And the analysis of the system, even in saturation, allowed us to retrieve some very important performance metric, like the throughput for each classes of jobs and the average number of servers that are idle or busy. Exact solution for both the cases we analyzed have been found before we studied the problem. We discovered it very late, though. But even so, the solution that was found was something very inefficient. They constructed the whole model, the whole generated state space as we were seeing before, and they solved it, which is very inefficient and has some very high computational limit. What we did was to study the one-or-all scenario where small jobs require just one servers and big jobs require all of them, like and this can happen, for example, for when we want conflict serializability in databases. And we were able to find a closed form and an exact and very efficient solution for this scenario. The other scenario we investigated is when small jobs require one servers and the big ones require a fraction of the available servers that we will call T. For this case, we didn't retrieve an exact solution, but we retrieved a very efficient and accurate approximation. The nice thing about this approximation is that it's very accurate when the parameters represent some real case study scenario. For example, when small jobs are faster and more frequent than big ones, as can happen in database management systems. In order to assess the accuracy of this approximation, we did the same thing the other authors did to retrieve the exact results, and we compared it with our approximation. So the red dots are the exact results, the line is the approximation. The nice thing about this figure is that here we pushed the speed of big jobs very beyond our model, our approximation assumptions, because it becomes really high, it goes over 100. And we assumed for this experiment that small and big jobs were equally probable. You can see that in any case, our approximation is pretty good. So, and this will help us to enhance the reliability of the approximation. This was a joint work with my advisor, Professor Simonetta Balsamo from Foscari, University of Venice, and Professor Marco Emone Marsan from the Indea Networks Institute. Speaking of Indea, is where I started to investigate the performance of distributed online gaming. I won't go deeper in this model because it's currently awaiting for double-blind review. But just to give some motivation and background, about 3 billion people globally play video games with their phones or tablets. And this is why networks management systems started to enhance the paradigm of gaming as a service. In fact, the game logic and video presentation usually takes place in a computing infrastructure in a cloud data center, and normally the user device just needs to give some feedback on the connection and register the commands from the user. The problem here is that only customers with a good network access and low latency can properly play the game. So we have a pretty demanding quality of service requirements, and the priority of this framework is low latency. Because of this, we experts and also we think that these technologies will be moved from the cloud to the edge. Why is that? Because of the intrinsic characteristics of these two technologies. As far as edge is concerned, we have that edges facilities provide more proximity with respect to the centralization that is usually put more farther away from the user with the cloud. Edge facility provides low latency and consequently responsiveness. They lower network traffic because not every operation needs to be sent to the cloud. And of course, because of this, they are cost efficient with respect to data transfer rate. Of course, they have a limited scalability though, because they have less computational power with respect to data centers. But since in online mobile gaming, the main priority is low latency, we think that we are going to move to the edge. What we were able to do was to create a stochastic model for edge gaming and to compute what we will call success probability for the communication between the two, which means that the commands of one user and the other are going to meet a deadline, a time deadline requirement, because of course we also have that when we are playing all together. And thanks to this definition of success probability, we were able to give a strategy for the best allocation in edge facilities for new connecting gamers. And then we also gave a comparison of this success probability both in the cloud and edge environment. As future direction, we want to expand this framework to a set of users, because for now, this success probability can be computed only for 2 users at a time. And we would also we want to also investigate the homogeneity of the quality of the experience experienced by the users. This means that when 2 users get spatially close in the game, we want them to also experience a temporal closeness in their interactions. This was a joint work with Professors Marco Aimone Marsan and Vincenzo Mancuso from the Networks Institute and Serena researcher Paolo Castagno from the University of Turin. Lastly, this is the work I'm currently working on, a network-friendly recommendation system. Just a glance. As we all know, content caches are ubiquitous on the internet. By storing popular content, they decrease delay, reduce costs, and improve the quality of service. We know that classic caches works as filters. So if we are sending a request for a cached content, we will have a hit, otherwise we will have a miss. With similarity caches, we have something different. We require content, and if we don't have the exact content but something similar, it's still okay. Of course, this decreases cost even more, but we have the problem of the happiness of the user. Will he be happy with the content we provided instead of the one he required? This is what we will call quality of experience. Evaluating the performance of caches by similarity is non-trivial, and even less trivial is to study a model that takes into account both the network characteristics and the features of recommendation system. Then among the various challenges associated with this project, there is the need to build a dataset containing information on every of these things. And then we also need to find a good trade-off between the quality of service offered by the network and the quality of experience that the final user witnesses when requiring a particular content. We built crawlers to capture information about availability of videos related to COVID-19 on YouTube with additional information. For example, for each video, we know in which YouTube server is being cached and the distance from the final user. Such information allowed us to estimate delays between users and the contents, and also distances in terms of similarity between all the contents involved. To the best of our knowledge, this kind of data set was not available yet. Taking advantage of this data trace, we are now building an analytical performance model that will be used along with this data trace to realistically evaluate the performance of a set of caching policies, with the final aim of investigating, as we were saying before, the best trade-off between quality of service and quality of experience, where the main metrics for this will be, for quality of service, the delay experienced from a network perspective, and as quality of experience is concerned, we will have the distance between the required content and the delivered one. Future direction for the works will want to integrate the popularity concept that is time dependent, because for now we have a photograph of this video and the popularity probability has been computed with the number of views for this video, which is, as I said, a photograph. We would like to integrate to make this model more dynamic, to be even more representative of real case scenarios. And it would be nice to create a general framework, like a real mathematical model that does not depend on any data trace. This is a joint work with my advisor, Professor Daniel Sadok and Jorge Salaveta from the Federal University of Rio de Janeiro, and a very talented master's student, which is Mateus Nogueira. I'd like to express my gratitude to my supervisor and every person I work with, without whom none of this project would be possible, and to thank a lot Professor Affetta and Professor Casanova for the opportunity, and you all for the attention.
Work for a PhD thesis.
I hope so.
Okay. Well, any questions?
Can you explain better the similarity, how you can use the similarity for the last, because I would like to know if we can do something.
So for the moment, what we did is that we have this data set with a bunch of entries, and we collected, translated actually the titles into English and the video description. We used that to compute the cosine similarity between the contents, so that we are able to construct the n most similar content list for every one of them. So that every time that a user issue a request, we are able to say, okay, we don't have that where you requested it, because maybe you are closer to this server, and in these servers we have this and content that are very similar to what you're asking. Take this. And this is more or less the strategy we are trying to use, and the kind of caching policy we want to investigate. So we go we will investigate both cases in which we give more importance to the recommendation we give, and other cases in which we go in the direction in which we want users